Okay, so why don't we get started with our talk for today for the Diffuse Gas and Cosmic Ecosystems SIG. Before we hear from our wonderful speaker, I want to just draw everyone's attention to the fact that the next talk is going to be in a slightly different date and time. So normally we do these on the 4th Thursday, but for October, we're pushing it to the 5th Thursday for scheduling purposes. So October 31st. And then I think it'll be, and it'll be 30 minutes later than usual. So normally it's at 4 p.m. Eastern time, and we're starting at 4:30 again for scheduling constraints. So that's going to be Harley Katz from the University of Chicago. And for our talk today, we have the wonderful Nick Battaglia, who's a professor at Cornell, although we didn't realize when we invited him that actually he's on sabbatical in Paris this year. So the time zone is slightly less favorable. But he'll be talking about some really exciting constraints on the CGM from new observations. So with that, Nick, I will give it to you.
Thank you, Erica. And yeah, I'm not at the office, as you can see. And the internet here is okay. So if it drops out, just let me know. I may have to back up a slide or two because
Okay.
I'll just keep talking. If you want, feel free to raise your hands. I can't see if you put anything in the chat right now, but if anybody has any questions they want to interrupt, feel free to do so. Yeah, so I'm going to tell you about some, I use the word new here a little liberally. These came out maybe a couple years ago, but there are some new results in here as well. But yeah, I really wanted to tell you about some exciting stuff that we're doing in the millimeter wave community, the CMB community, in terms of what we can do for the circumgalactic medium. And this isn't just work by myself. I've listed two graduate students, Emily Mosier, who's since graduated and moved on to industry, and I'll show you some preliminary work from Chad Popick, as well as Stefania Amodio, who was a postdoc working with me and then moved on to Strasbourg, and now she's working in industry. And then some other folks, Simone Ferraro, Emmanuel Shine, and the whole ACT collaboration. So I was told that you're all circumgalactic medium experts, so I'm not going to motivate why the circumgalactic medium is interesting. However, I will take this opportunity to tell you that we're not going to be probing maybe the circumgalactic medium that you're used to. Okay, we're going to be probing the outer circumgalactic medium, right? So this is out to the virial radius and beyond for these measurements that I'm going to show you, into the sort of boundary between the circumgalactic medium and the intergalactic medium. So I'm going to call this the outer CGM. I'm just going to refer to it as a CGM, but I'm mostly referring to what I would call the outer CGM. So we're talking hundreds of kiloparsecs out to megaparsecs. And so that's outer CGM to the virial radius, beyond into the intergalactic medium, and that boundary in between. Okay. Okay, so as I said, new observational window into the CGM, and hopefully I'm going to introduce this to you, and then I'm going to talk about what we can learn from these observations in terms of what can we say about sort of physical processes going on in the circumgalactic medium, things like feedback. And I'm also going to tell you about some interesting comparisons that we've been doing to numerical simulations, and then I'll look forward and tell you about some observations that are coming up, and then some experiments that are coming up that will actually further these endeavors I'm going to mention here. Okay, so we are going to be using the cosmic microwave background. So this is a picture that you're probably very familiar with. This is an image from the Planck satellite of the CMB as observed by Planck. And what you're seeing here, right, are photons from the surface of last scattering when the universe was neutral, and then, went from being a plasma to neutral. And these photons, you're seeing them as they last scattered off those electrons and free streamed towards us. Now, this image here, right, you're seeing positive and negative temperature fluctuations. You're seeing hot and cold spots. Right, these are the initial seeds of structure growth in our universe. You can think of them like our initial conditions, right? And from these fluctuations, right, the structures that we see today, such as galaxies, galaxy clusters, grew and evolved from these tiny, tiny fluctuations, right? These fluctuations are some of them are 1 part in 10 to the minus 4, right? So this image here is really, really stretched. And in fact, if it wasn't stretched, it'd look a lot like this. And so the CMB is actually a fairly uniform backlight. And that's actually what I'm going to be telling you about. I'm going to be using it as a backlight. I'm not going to be talking about those primary anisotropies that I showed you on the first slide. Now, just to illustrate sort of what's going on, right? I said those photons free stream towards us, but that's not exactly what happens, right? So this is a little movie illustrating what a path of a photon may be coming towards us. So you're not going to hear Charles Lawrence. He has a much nicer voice than me, but you will be hearing me. So what you're seeing here is photons bouncing around in our hot, dense plasma early on in the universe off the electrons. And then you'll see these electrons recombine with the protons, and then all of a sudden these photons will start to free stream towards us. And you'll notice as this photon is free streaming, you'll notice changes going on in the background. You'll see first stars starting to form. You'll also notice that as the photon is traveling through the universe, right, it's being redshifted, right? So the wavelength is getting longer. You see the energy going down, and you also see the photon not come straight towards us. You'll see it be deflected by matter. So this is gravitational lensing of cosmic microwave background photons. And you'll also see this little interaction here where this electron gets Compton, or so this photon gets Compton upscattered, inverse Compton upscattered by a free electron. It's going to get gravitationally lensed again, and then it's going to come towards us. So this is an example of what a path of a photon may take from the cosmic microwave background to us, right into the Planck satellite. Okay, so the whole idea here, right, is we're going to be using the photons from the cosmic microwave background as the uniform backlight, and what they're going to illuminate, well, illuminate many things, right? Anywhere there's free electrons, right, you can get these sort of scattering events. You can get Thomson scattering, you can get inverse Compton scattering, you can get Doppler shifting of these photons. So I'll tell you about at least two of those. And so, during the epoch of reionization, we can probe with this uniform backlight of the cosmic microwave background. We can also look at the growth of structure, right? And we can also look at astrophysics. So I'm mostly going to tell you about astrophysics, but there's many, many other things that we can do with these photons, right? And the telescope or the observations we're going to tell you about is the Atacama Cosmology Telescope, or ACT. So ACT was a telescope at 5,200 meters. It's since been taken apart and taken down. It's no longer taking data. And this is in the Atacama Desert next to Alma. And the reason why we went all the way up there, right? It's a very dry place. And if you want to observe cosmic microwave background, right, you want the atmosphere to be very, very dry, right? We don't want any water absorbing these CMB photons. And it's a decently sized mirror. It's a 6-meter primary mirror. And you can see it here. Here's the primary mirror here. Here's the ground shield, so we don't get any stray light or anything like that coming into our focal plane, which is hidden somewhere down in here. And yeah, and it just observes the sky, and it's a survey telescope mainly going after the cosmic microwave background. But I'll tell you how we used it to actually probe things like the circumgalactic medium. Okay, so to give you an idea why we like ground-based telescopes, and I showed you, a CMB photon going into Planck. Well, on the right here we have a Planck map, and on the left here we have an ACT map. And this is sort of similar qualities you see from the South Pole as well. A South Pole telescope's a little bit bigger than ours, but it's at the South Pole, so we can cover a little bit more area. And what you see as we here, this is the same map, and we're scrolling across, and you'll notice as we scroll across, you'll see a lot of noise here, but as we scroll across, you'll see smaller things start to be picked out, and this is basically because we have the resolution to resolve these structures. So what you're seeing here, right, these are point sources, these are dusty galaxies, but you'll also notice some sort of little cold holes here, right? Those are galaxy clusters that we're actually seeing these various inverse Compton scattering effects happen in. So I'm just going to play it a little bit longer, but just to get the point, you can see much noisier, poor resolution here. On the ACT side, the ground-based side, where we can deploy much bigger mirrors, you can really see the high resolution, lower noise on much, much smaller scales, spatial scales than Planck. And there'll be some experiments I'll tell you about going forward where we can get sort of this sort of resolution, but much, much deeper. Okay, so what exactly are we looking at? Well, we're looking at least for this talk, I'm going to be telling you about two effects. They're both called SZ effects, Sinyavs-Leldovich effects. One of them is the inverse Compton scattering, as we saw in the movie. This is when a CMB photon comes in. interacts with an electron. The electron doesn't even really notice it, but the CMB photon gains energy and is inverse Compton upscattered. This causes a unique spectral distortion. I'll show you a little bit better illustration on the next page, where you have a deficit of low energy photons and an excess of high energy photons. These CMB photons can also be Doppler boosted. So let's say these electrons have some peculiar velocity with respect to the CMB or the expansion or the Hubble expansion of the universe, right? Then these CMB photons will be, if they interact with these electrons, they can be Doppler boosted. And what's really neat is that these two effects probe the thermal SC, the TSC probes the integrated line of sight pressure of these free electrons, and the kinetic SC, this is the Doppler boosting, probes the line of sight momentum. Okay, so I want you to keep those in mind as I tell you more about these. And these effects are small, right? They're at least an order of magnitude smaller than those primary fluctuations I showed you. This is the thermal SC for a galaxy cluster is about 10 micro-K fluctuations. The kinetic SC for a similar size object is about 1 micro-K, right? So this is about 2 orders of magnitude smaller. It's actually really hard to see, and we only really got to see it in the past decade or so, at least to measure the kinetic SC effect. Thermal SC has been around for a while. Actually, the first measurement was actually made before I was born, so that's a while. So here's the thermal SC, the TSC, right? Let's say we have our primary CMB fluctuations. You throw something like a galaxy cluster in it. Here's those deficit of photons at 30 gigahertz, right? So there's a hole or a shadow at 150 gigahertz. At 217, there's a null, right? Where there's actually no distortion. And then on higher frequencies, you get this excess. So there's more electrons up there. So this is just showing you an actual observation of a cluster in Planck. You can see the deficit, right? At these lower frequencies, there's the null where you don't see it, and then you can see the excess at higher frequencies. The kinetic SC, right? This is the Doppler boosting of CMB photons, right? And you can imagine this Doppler boosting to depend on your direction of your velocity, right? Some galaxies will be moving away from us. This will cause them to look colder, right? The CMB photons, and if they interact with a galaxy moving towards us or any free electrons moving towards us, they will look a little hotter, right? And so this effect depends upon your integrated optical depth, right? Similar to the TSC, right? This Compton Y parameter is the integrated pressure along the line of sight. So that's the optical depth times the temperature, the optical depth to CMB photons, right? And here you're going to get the optical depth to CMB photons and then the line of sight velocity, right? So this is your momentum, your line of sight momentum. Okay. And as I said, the KSC has been really hard to detect. The TSC we've seen for a while, a long while, but it was only really in the past decade that we were able to see the kinetic Sinyavov-Zeldovich effect through various different methods using various estimators that took advantage of the fact that galaxies have velocities can be moving towards each other. So these so-called pairwise statistics. There's also something else called the velocity reconstruction method I'll tell you about here. There's another method where you can actually look what's called a projected fields method, where you actually square your CMB temperature. And the reason why you need to come up with these interesting estimators is because the velocity, right, galaxy velocities can be moving towards us, they can be moving away from us. It's sort of a parity odd field. So if you were to just take a bunch of galaxies and try and see the kinetic SC effect, half of them may be moving away, half of them may be moving towards us, and they will all sort of cancel out. So you have to be really, really clever here, right? So we have our optical depth, which tells us about astrophysics, and their velocity basically tells you about the gravitational potentials these galaxies or these free electrons are falling into. Okay, so this basically probes cosmology, the velocity over here, and the optical depth tells us about the density, right, of these free electrons. So that tells us about astrophysics. So we can make sort of two different measurements here. We can look at sort of velocity correlations. So if you're interested in cosmology, you want to look at velocity correlations. So the relative velocities of these are the statistics of the velocities between these galaxies. Or if you can do some sort of aperture photometry where you can actually probe out from the galaxy. So you somehow have a way to get rid of this velocity and just look at the density here. You can actually probe astrophysics, okay? And so this is the method that I'm going to tell you about here. This is called a velocity reconstruction stacking method. This was proposed initially by Shirley Ho and collaborators back in 2009. And so what you do is you take your CMB map and you take a velocity reconstruction or an estimate of the velocity reconstruction for, say, galaxies. Now, this velocity reconstruction is something that's done all the time in cosmology. Surveys that use the baryonic acoustic oscillations do velocity reconstruction all the time. It's basically you look at the distribution of galaxies, you determine where the overdensities are given the densities of these galaxies, and you can sort of move back and say, it must have fallen in this way, that way. This means that this galaxy is moving, at least on large scales, right? So you can make some sort of linear estimation of what the velocity field is on large scales here. And so if you correlate the velocity field with at the positions of galaxies with these with your CMB map, if there's kinetic SZ in here, you'll get velocity times velocity, you'll get velocity squared, and then you can look at this sort of cancels out that velocity. This becomes an overall normalization factor, and then you can look at the density profile as a function of radius, and that's what I'm showing you here. This was first demonstrated on real data by Manuel Shen, Simone Ferrara, and the ACT collaboration. So this is showing you an average sort of cumulative density profile, comparing different models for what the gas profile may look like, if it looks like dark matter or some old simulations that I ran. Okay, what's really neat about this estimator is or at least the kinetic SZ effect in general, is it's an unbiased estimator of the free electrons. And what do I mean by that? It means that if you are a free electron, we will potentially see you, right, like this. It doesn't matter if you're hot or you're cold, right? It's just if you're a free electron and you have some peculiar velocity, you will have a kinetic SZ signal. Okay, so that's really nice. Whereas some other estimators, like, I don't know if you measure this through the thermal SZ, that's going to be temperature weighted, or you're actually just measuring pressure, right? Things like X-rays, you're measuring densities squared, right? So this is unbiased, a nice unbiased estimator of a free electron. Okay, and so this happened. This measurements happened while I was at Princeton with Simone and Emmanuel. They were graduate students at the time. I was a postdoc, and we got talking about what could we actually learn from such measurements. And we wrote a paper basically saying, well, if we combine TSZ and KC measurements, what can we actually learn? And right, so you have pressure and you have density over here. So you combine pressure and density. Well, some people wrote about this 10 years before, saying, well, you can get the temperature, get the optical depth, you can basically decompose all the components. But we turned it around a little bit and said, well, can we learn anything about galaxy formation? It turns out you can. And in fact, the CGM. Now, in hindsight, we probably should have mentioned the CGM in our title, or at least in our abstract, but looking back on it now, we were really talking about how you can actually probe the circumgalactic medium with future measurements of pressure and density. And it didn't take long for actually us to do that in reality. So here are these newish measurements that I said I'd tell you about. So what we did was we took the BOSS catalog. So this is a spectroscopic sample from SDSS of CMass galaxies. So these are supposedly constant mass LRGs at redshifts of 0.4 to 0.7. And we did a velocity reconstruction on them. So there's about 400,000 objects here. We say they're massive galaxies, small groups around 10 to 13 solar masses. Let's see if we can get a little animation going. Right, so here are the galaxies in the BOSS CMass sample, and then you'll see a velocity reconstruction of them. So this would turn there you go. So blue is moving towards us, red is moving away from us. You can actually see structure in this, right? And that's because the velocity scale, the correlation length of the large scale velocity field is about 50 megaparsecs. You can actually see that in the velocity reconstruction. And so we took those galaxies and we cross-correlated them with our latest, at the time, our latest ACT maps. So these were our DR5 ACT plus Planck maps at 150 gigahertz and 90 gigahertz. We also looked at some component separated maps, and I'll tell you maybe a little bit about them. And so just to illustrate what we actually did for our measurement, right? So this signal is small, right? I already said for a galaxy cluster, it's already an order of magnitude smaller than the fluctuations we see in the cosmic microwave background. So you can imagine for a galaxy, at least for the thermal SZ, it scales like mass to the 5/3. So it's way, way weaker. For the kinetic SZ, it actually scales like mass. So for an individual galaxy, right? So this is just stacking. I was playing around with this actually this week just to illustrate this for you. You don't really see anything, right? There's no real, maybe you can say there's something there, but it's comparable to the noise that you see in this map. This is actually a component separated map. And you'll notice that the axis here, it's actually, fairly high if you think about the Compton Y parameter. So this is mostly noise, but we have 400,000 galaxies, right, that we get to look at here. So what we end up doing is we take all these individual stamps, right, and we stack them up at the same location. So the galaxy is always at the center, right? If we're doing kinetic SE, the stack is weighted by its velocity, so we don't get that cancellation. For the thermal SE, we don't have to do that, right? And so we stack up all these galaxies, and eventually what you get is something that looks like this. Now you notice the scale here, right? 10 to the -7. So this is why we don't see it here. It's much, much smaller, but because the only thing that should correlate with the position of the galaxy is the signal coming from the kinetic SZ or TSZ in the absence of, say, dust or something like that. And that's another story. I'll tell you about that. You should get a signal that pops out, right? You'll beat down this noise by square root n, right? And so you can see, we need to beat down about 2 orders of magnitude in noise. So, we can easily do that with 400,000 galaxies. And we do. This isn't the actual measurement. This is just, I picked some random galaxy sample and pulled out a TSC stack. So you can see this is the thermal SC from some random sample of galaxies in BOSS. So this is what we're doing. We're making a statistical measurement, right? So this is an ensemble measurement of the pressure in these galaxies. Now, there's some pros to that, and there's some cons to that, right? The pros is that we have a whole ensemble of galaxies. We can look at the statistics of these galaxies. We can look in simulations and look at the statistics of those simulations and compare like that. Some of the cons are it is a sample of galaxies, right? So you need to actually, if you really want to understand this sample, you actually have to model it properly. And I'll get into that too in a little bit. Okay. So here's the actual measurement. It's not an illustration like I was showing you here. Here's the gas density. You can see it. It's it's there. Here's the gas pressure. This is similar to what I showed you on the previous slide. And here's just the raw pressure, right? So this is the raw TSC. This has been component separated. And you'll notice that there is actually dust in the center, right? You can see almost this donut here. And that's because in the center, right, there's a bunch of galaxies, and galaxies actually have dust, and dust is emissive at these frequencies, right? So we have this dust emission in the center. You have to be very careful about that. And we did some modeling for that. I may mention it later on. But here are the measurements, right? So we have gas density, gas pressure, gas density through the KSC, gas pressure through the thermal SC, right? And here's the zoom in of a galaxy. It's probably not any of the galaxies that we stacked in here. Okay. A couple things to notice, right? So this is showing you roughly the inner circle is showing you the beam. The outer circle is showing you roughly the virial radius. And so what you'll notice is that we have, in some cases, depending upon which map we're stacking here, we'll see we have several elements inside the virial radius, but you'll notice there's a halo of gas, or at least hot gas, right, extending well beyond the virial radius. You'll notice a little bit of that here too, although it's a little hard to tell, given that this is a little bit lower signal to noise than the KC is lower signal to noise than the TSC. So in order to pull it out and actually, try and do some work on this, because we've stacked, these things are essentially spherical blobs. So we can do, basically aperture photometry to extract the flux from these galaxies. So that's showing you here. So here's the KSC flux as a function of radius from the center at 90 and 150 gigahertz. Right, you'll notice they're a little slightly different, and that's because they have slightly different beams. But in general, once you get further out, they should agree with each other. There should be no sort of spectral dependence here on the KSC and TSC. Now, one thing we did, because some of us are cosmologists, is we wanted to show that the gas doesn't look like dark matter. And talking to a lot of you galaxy formation people, you guys probably know that, but you'd be surprised what cosmologists do when they model dark matter and the total mass in the universe. So we decided to show that the gas profile anyways looks nothing like this, and this is a cumulative profile, right? So that's why you see it keep rising. The cumulative profile looks nothing like the dark matter profile. So the gas is a lot more extended than the dark matter, right? A lot less peaky. Okay. So that's the density profile, cumulative density profile, right? Here is the cumulative pressure profile, right? It is negative, right? Because we're looking at this is at 150 gigahertz, right? So we're looking at negative temperature fluctuations, right? So that's why it's negative, right? So the more negative you go, the more pressure there is. And again, these are very sensitive to dust emission, which is why having higher frequencies, like an experiment that I'm helping to lead on the Fred Young Submillimeter Telescope called CCAT, will be very important to have these higher frequencies in order to remove the dust and make use of these, future observations that we're going to have. We have temperature, we have pressure, so you can do the natural thing and get some sort of average temperature. So this is showing you the temperature profile, the average temperature profile of CMAS galaxies out beyond the virial radius into the intergalactic medium here. And so this line here, this dashed line here, is roughly the virial temperature, and you can see that we're subvirial outside the virial radius, and it decreases slowly. But as you'll see, this is a little hotter than we'd expect if you compare it to simulations. Okay, so this is a density weighted temperature, right? We're taking the thermal SE, we're dividing it by the kinetic SE. So you can see here we have tau, optical depth times temperature, and the kinetic SE, we basically have tau. So we have a tau weighted temperature, density weighted temperature. Okay, so we have these profiles now. We have these average profiles, and I said it is very important that we have some way to model these stacks. So the first thing we did when we got these was develop a pipeline to analyze these observations. So this was some software that Stefania Amodio created with me when she's spending her time at Cornell. And basically what it did was it took a 3D profile, a spherical 3D profile, and it took that and we forward modeled it into the observable space, because we really want to compare an observable space. That way we don't have to do anything with the error bars or anything like that. And it's much easier to take a pristine theory model and compare it to your observations in observation space. So this is what we did. We developed this forward model where you take your 3D profile, and it can come from anywhere. It can be an analytic profile. You can have you can take some simulation profile, whatever you want. You can run it through this, and you should be able to make a prediction, right? So first, what you do is you project it, you convolve it with the beam of the experiment, and then you do your aperture photometry, and then you get out your thermal SC down here in red and your kinetic SC here in blue. Okay. And this gives you these cumulative profiles. Now, there's a little bit more to it, but this is just illustrative. And I'll maybe get into that. One important thing, and I'm going to stress this a couple of times, is how you do this initial profile that you put in is very important. Because you're modeling a sample of galaxies across different redshifts, and they have different mass ranges, especially for the thermal SC, it is very important that you include some sort of population modeling for your galaxies. The thermal SC has a nonlinear response to mass, so taking an average mass would give you the wrong answer. There's also other terms in this, like the 2-halo term, that's really important as well when you're modeling this. And so Emily looked at this. This is just showing you that if you make different, I'm not going to go into the details of this because I still have a little bit more that I want to tell you. But basically, if you don't do the right thing, you're going to get the wrong answer, right? So this is showing if you don't include things like the 2-halo term, if you don't properly average over the mass or weight by mass of your galaxies, you're going to get the wrong answer. Okay. Something that was really fun that we did too was we took an analytic model. Now, this was an old analytic model by Oestreicher, Bode, Babul, designed for galaxy clusters. But what was neat was it had, you could inject energy into this model and it would change the intercluster medium. So we applied it to the circumgalactic medium. But it also had non-thermal pressure as well. So we were able to put some constraints, model-dependent constraints on how much energy given this model was injected into the system and how much non-thermal pressure there would be in this system. So about 30% of the total energy we estimated, and this is again model dependent statement, had been injected by feedback. And then we estimated that there's less than 20% of the total pressure in the system was non-thermal. This could be magnetic fields, cosmic rays, turbulence, things like that. So this is kind of a number that makes sense, at least on the galaxy clusters side, right? You expect maybe 5-10% non-thermal pressure in these systems. But down on the galaxy side, we actually have no idea. So this is a useful upper limit. Now, the really neat things that we did after this, we wanted to make a little less model dependent statements. I guess we wanted to compare it to sort of state of the art simulations. So we took a couple, at least ones that we were easily able to grab, some of my old simulations, and then some by the illustrious T&G crowd, and we ran them through. We did this population modeling. And you can see here that they actually don't do so well. The density doesn't quite do okay. Now, I will caution you these error bars because we're doing aperture photometry, and once you really get out here, you're really starting to get CMB fluctuations here too. They're highly correlated, so there's covariance matrices where these outer bins are extremely correlated. So Kai-Bai is not suggested. But the density is actually not that bad. But I'll show you a case where it actually gets a little worse in new measurements. But you can really see out here, these aren't so correlated. The pressure just doesn't really fit. The simulations are not hot enough in the outer CGM into the IGM. They just don't work. And so this was a puzzle to us. So we said, well, this is one set of simulations. Can we do something else, right? This is one set of simulations with one feedback prescription. Here it is. If you're not used to looking at these sort of cumulative, density profiles and pressure profiles, here it is in as a theorist would look at it, right? A nice spherical radial profile. You can actually see here this band tells you sort of the allowed regions for the density fit that we had, and you can see they actually do pretty good in the region where we actually have measurements. Here is the pressure, and you can see basically with the band, nothing really falls in that band. So this is sort of the illustration of what I was trying to show you in more of a theory-friendly space. So this is a puzzle. And we said, well, let's play around with this. There's these camels simulations came out. We were actually able to play around with various different feedback parameters. So this was a large suite of simulations where they messed around with cosmological parameters as well as feedback parameters. And we tried to see if we could come up with an emulator to try and fit the density profile. We found something that worked. Both CMB and both in TNG and Simba, it fit okay, but those best fit density profiles when you put them into the pressure profiles just didn't work. So we found some cases where give them some interesting feedback parameters. Again, this is work by Emily Mosier in collaboration with folks in Camels like Erwin Lau and Daisuke Nagai, where we were able to get things to fit, but the pressure, again, we just couldn't get it to work. Simba actually came the closest. And Simba has, for those of you who know these large cosmological simulations, Simba has a very extreme sort of feedback, and the one that fit the pressure did not fit the density. So these aren't the same, right? We fit them individually, otherwise it would not work. So this is a puzzle, right? why are these simulations, or why, the simulations, at least that we compared to, sort of underpredict the CGM pressure at these large radii? Uh, you know, is it how energy is being injected? Is it how energy is being propagated? Maybe there's some things like, potential two-phase. There's probably a two-phase circumgalactic medium. I wouldn't be surprised. Multi-phase circumgalactic medium that's not being captured in these simulations. That may be something. But one of the things we did, instead of trying to really question the simulations, was actually go back and say, hey, what if we messed up? What if we missed something in the theory modeling? And this is actually what Emily spent the rest of her thesis doing, was going back and seeing if there was anything that we could do, any sort of modeling choices, anything like that that could change it. And so we went looking for more systematics. And so Emily did a very detailed systematic study. And this ended up being a very large chapter of her thesis, looking for various things that we can do. What if we change the beam? Because there's a little bit of beam uncertainties, various different things. And we just couldn't find it. Anything we did was very, very minor change. We looked at different convolution methods. We changed the line of sight integration ranges. Again, the changes were very, very minimal. And one thesis was not enough for this. Chad has continued this work, and he's looking for even more systematics that we could have missed. So Chad is now looking at even higher fidelity galaxy modeling techniques. So things like having a HOD modeling centrals and satellites very differently. He's even put in miscentering. What if the gas is slightly miscentered? Can we get these extended things? And everything we've looked at's actually gone in the wrong direction. So the changes are small, and they appear to be very minimal. And this is just an example of Chad playing around with various parameters in these HOD models. But he had to go to a very sort of extreme away from like the CMAS sample in order to get this. The problem with these HODs, at least as it is for the CMAS sample, is the CMAS sample tends to be, there's not that many satellites, and there's a lot of centrals. They're very, big, massive, luminous red galaxies, as they were selected to be. So it's really hard to play around and get, at least with these HOD parameters, and get things that could give you, if you crank up the satellite fraction, it actually decreases it because there's no actual satellites. They're all mostly centrals. So dust corrections are very important, but we've been looking at this for now, given the sort of fidelity of our measurements. But future measurements, we look even more into the dust corrections that we did in the past. So it still remains a puzzle. Again, Chad has found very minimal changes, even with things like miscentering. You have to do very extreme miscentering models to get changes. And again, those go in the wrong direction. They don't give you more pressure. They actually give you less pressure. So we're looking into this. So this is still an open puzzle on our end. But again, we're trying to make these measurements. We're making new measurements, and we're going to, this modeling that we're doing now is going to become even more important as the error bars get smaller and smaller. So I don't think it's too much of a surprise, though, that maybe the simulations didn't quite get this right? Predicting gas profiles on these scales is potentially pretty challenging. You need, you need to have really high resolution, and you need lots of galaxies to do this. So you need high resolution, large boxes. These observations that we had were actually new, right? We're probing a new regime of the circumgalactic medium in terms of its pressure and density, right? We're out to much larger scales than previously probed. I don't think I finished my thought here. So, but one of the things that's kind of neat is that there could be a nice feedback loop here where we actually can use these models to help inform maybe future subgrid feedback models that go into these simulations. But we will see. And as I said, there are newer measurements. So this actually came out this summer, and the puzzle still persists. So these are measurements led by Boriana Hadzicka. And this is now using a much larger sample. This is the DESI sample, but it is still a sample of luminous red galaxies crossing with ACT. And we've gone from the KSE measurements that I was showing you before, about 6 to 8 sigma, depending upon how you count. This is a 13 sigma detection of the kinetic SE in these galaxies. The air bars are nice and small. And what you'll notice here is the simulation that matches this the best is the original Illustris. And that's because, there's actually a deficit of gas, as we showed in the other ones in the previous CMAS sample. And for those of you, again, that are familiar with simulations, Illustris had a very extreme sort of feedback. And in fact, the feedback was so extreme that, things like galaxy clusters at redshift 0 did not have any gas in them. So this is probably not what's going on, but this happens to be the best that fits at this mass range and this redshift. So this is neat, right? We have these new observations and this puzzle still persists. So that was KSE. We actually have new TSE measurements coming out. This is just an example. This Chad did some stacking earlier on just to show you how much better. So this is an example of what the CMAS stack would look like or did look like. And this is what we expect to get in DESI. You'll notice that there's the noise levels in the map are much, much lower. Again, this is not what the actual result is going to be. The actual result is work led by a graduate student out in Berkeley, working with Simone Ferrara and Emmanuel Shen, and they have a result that's going through the review process within ACT and DESI at the moment. And it is a really high signal to noise result at multiple different redshifts. So that's really neat. And not too surprising that, we're going to have a much higher signal to noise than we had for the KSE as well. And these are all being done on ACT's YMaps. So here's an example of, or this is the latest ACT YMap. This is just an advertisement for it. And these maps are public if you want to go and grab them on Lambda, and you can play around with them. And this is work led by Will Colton and ACT. Okay. So there are future telescopes coming up. There's the Simons Observatory, which should be starting observing 2025. It is similar size telescope, 6-meter primary mirror, but it has a very large secondary mirror, almost the same size. And here you can see this is so it can do really large areas and be a really nice survey telescope. There's multiple components of the Simons Observatory, but this is the telescope that matters for the secondary science, right? Or the science of C and B secondaries, I should say, not secondary science. There's a similar telescope that's going to be even higher. This is the Fred Young Submillimeter telescope as part of the CCAT collaboration. And why we went a little higher for this telescope is we're going to go to much higher frequencies, and this will really help with the dust. So we're about 400 meters higher, roughly, than the ESO site, which is the same as the ACT site. And this really allows us to actually scan the sky and map the sky at much higher efficiencies than lower down in the plateau. PrideCam isn't quite as big in terms of its, and it's multifaceted in terms of what it's going to do. There's going to be a spectrometer, at least one, maybe two spectrometers on it. And here's the frequencies that are funded: 270, 350, and 850 gigahertz. And there's a plan for a 410 gigahertz channel on this telescope. So really giving us, millimeter into sub-millimeter. And this will be slightly different technology than what the lower frequencies use. So they're using TES bolometers. Here we're using kinetic inductance detectors, so KIDS. So given that we have these newish telescopes coming on the sky, or at least we knew they were coming, Colin and I decided to write a white paper for the decadal, projecting sort of what we saw, how we would use millimeter wave observations to probe things like feedback and galaxy formation. Here's the archive number. I show you this plot to say that we made a big mistake in these are forecasts of signal to noise over the next couple of years in kinetic SE observations for a particular estimator. And we made the mistake of not making these forecasts for much further out in the future. So let me just correct some of these numbers here. And there, that's a little better. So at least this is still far enough away we can obtain it. But, we are roughly getting around, tens of signal to noise of tens in the year 2024. And we hope, and we should be getting, a couple more factors as we move into 2025. And then 2028 is far enough away, although this number might be a little scary here. And one of the things we wanted to highlight here is that the thermal SC and kinetic SC, it is an average measurement, right? So you're getting sort of an average profile, but it is really sensitive out to, all sorts of different redshifts. We sort of blop down these roughly these blobs of where certain probes of the circumgalactic medium are sensitive to. And this is where we also picked, there's another dimension, which is the radius. We did pick the virial radius because it's more advantageous for the thermal and kinetic SC. But basically, if you have a sample, you can pretty much get a large enough sample. You can pretty much get a thermal and kinetic SC signal from it, given what we expect coming out of the Simons Observatory and CCAT, and then eventually things like CMB stage 4. And then you can really do some really neat science, right? So forecasting a little ahead, this is what we did back in 2017. We can get sort of sub% level pressure profiles and percent level density profiles in these galaxy samples out to the virial radius and then beyond. So we're getting, slightly higher resolution, not quite, but much lower noise and much larger samples. And that's what's really leading to these improvements in these measurements. And then you can really say, well, if you have these sorts of, super high signal to noise, super low or super small error bars, you can really start to divide things up, maybe do subsamples, right? You can do, we've mostly been looking at LRGs, but you can imagine maybe a subgroup of star-forming galaxies. You can bin this up as a function of redshift. You can split this up as a function of mass. And so this is what Colin and Marcelo led in the CMBS4 Decadal Science Review, I believe, or the DSR for short. Basically, given the error bars that we expect to get from something like CMB stage 4, a decade from now, all the current models of galaxy formation will probably be not viable given just the tight constraints that we have over these small redshift ranges and small mass ranges shown here. But we already at a sort of interesting tension with the current simulations. Then Emily took these forecasts and said, well, let's go back to our emulator and see, can we constrain things like feedback? This is, at least on the subgrid model scale. So can we actually inform the simulations, as I said? And the answer is yes. You can actually get some really tight constraints if you want to turn the observations around and use them to inform how the subgrid models in the simulations should work or should be tuned. So yeah, I think I'm a little bit over time, but let me just leave you with sort of a picture summary of what I told you, right? So CMB cross correlations, SC cross correlations are this new window into the outer circumgalactic medium, constraining density profiles and pressure profiles. I showed you some interesting things you can do to constrain feedback. There's some really, really neat things you can do if you also get lensing information. You can do sort of these non-parametric models, but I didn't have time to tell you about that. And then, in these comparisons with numerical simulations, there's a really nice sort of synergy, but also a tension with our current measurements and what the current numerical simulations have predicted for what these sort of outer CGM thermodynamic profiles are looking for. So I'll leave you with that. And just to say, this is just the beginning, right? These measurements are, despite our inability to forecast far enough into the future, these measurements are currently taking off in terms of their signal to noise and fidelity. So stay tuned for more interesting results coming from the millimeter wave community. So thank you.
Thank you, Nick. That was really interesting. Do we have any questions from anyone? You can raise your hand or you can just unmute yourself and go for it. Jake, go for it. And then Yakov, I see your question in the chat, so I'll ask that next.
Hi, Nick. This is a really nice talk. I was wondering what you think, I guess, for is the fact that we're having low pressure in simulations at large radii, is it, but the density is not as far off? Does that suggest we're kind of, the models currently are throwing roughly the right amount of material out, but they're just not heating it up enough? or what would be your interpretation?
I think it's really hard, right? If you think about like the balance there that you have, right? It's really, if you're getting the density right, I guess it's hard and sort of just this sort of standard way of thinking about it to really heat it up anymore, because you might disturb then the balance between the gravitational potential and the gas. So I think, if you think it pure from like a hydro standpoint, it's hard to solve. But I think if we think a little bit more about the microphysics, it might be in the microphysics and how we're doing this. So it may be possible to get or heat up the very diffuse hot gas and still have the right density if you have, say, these coldish clumps and things like that. So that may be one way to do it. But that requires you to have a multi-phase medium on these scales. And I know there are some simulation groups working on this. I've been chatting a lot with Drummond, although I left for sabbatical when he arrived at Cornell, but we had been chatting before that about ways that this could potentially work. So that's one of the things we're going to be looking at going forward, is if these sort of newer sort of treatments of the CGM in these sort of cosmological simulations can sort of capture what's going on here. But yeah, I mean, I wish I had an answer, Jake, but I mean, this is just me spitballing. That's one idea. There may be some others. I know there's some modelers on here that may have some other ideas about potentially what could go on here. There may be other ways, if you're heating the gas up via like cosmic rays or something like that, to get it hot and keep it hot and still get the right densities. But again, I don't know. It's a puzzle, and I think it's a neat puzzle.
Thank you. Yeah, I'm collaborating with Drummond on the stuff that you're talking about, so that's why I'm quite interested. I'll hopefully come and visit him at some point. And
Great.
Okay, so Jakob's question in the chat, thanks for the very interesting talk. Do you think it might be possible to say something about the azimuthal variation of density / pressure in the sample from the stacked image? The extreme scenarios being spherically symmetrical CGM versus 2 jets or lobes in each galaxy that add up to a symmetric image due to random galaxy orientations.
Yes, great question, Jakob. So there's no orientation going on here, and there's enough galaxies being stacked that they do, even if you do have jets and things like that, or some sort of asphericity, it does come out to be spherical. And we've tested this in simulations and things like that. But you do raise a very interesting question, and something that I'm actually in the process of trying to address. And one thing would be really neat is if we could figure out, and I think there's some proxies for which way we think the jet's coming out. We can do an oriented stack, and people are doing this with large scale structure. So they're doing this mostly to find filaments. So they're looking at like how galaxies or galaxy clusters are being fed, and you can actually see these nice filaments come in if you do an oriented stack with a large scale structure. But you can imagine doing something smaller, thinking about like the galaxy. You could look at the galaxy ellipticity, right? And you can imagine that if it has a jet, it probably, maybe not, probably perpendicular, right, to the spin axis of the galaxy, sort of the shear that you'd measure. And so you could do something where you could get an oriented stack and maybe see sort of aspherical outflows or conical outflows coming out from the galaxies in terms of both pressure and density. Now with the density, you may also get some maybe contributions from, say, rotational KSC. So that would be one thing that we also need to see. You can maybe see these disks rotating, but you'd also have to know the spin. But you could potentially see sort of, as you mentioned, sort of outflows coming out off the galaxies if we were able to orient them along sort of the jet axis. That's to be done. I think it's definitely a doable project. Maybe a graduate student, couple chapters of a graduate student thesis.
So Jakob says, cool, great stuff, thank you. And then Ben Oppenheimer also has a question in the chat. Nick, what about future lower mass and lower redshift samples for SC? And second, how could a 2-phase CGM you mentioned solve the challenge of the CMAS signal?
Okay, so I'll get the second. I think I postulated how it could potentially solve when I was talking to Jake, but the idea would be you could still maintain the right density, right? If you contain some of that density in the cold clumps, then you could really heat the sort of diffuse, hotter circumgalactic medium to get the temperatures a lot higher, and you'd still have potentially the densities. But yeah, I could see maybe it might not work. Again, this is just speculation, Ben. So you may have some ideas. I wouldn't be surprised. But to get to your first question on other samples, so we are looking at their, DESI has a low redshift sample. There's also a low redshift sample in BOSS that we can look at. There are currently plans within ACT to look at these lower redshift samples. Going down lower in mass is also a possibility. It'd be nice if we had a good low mass spectroscopic sample if we really want to get the density as well. So maybe this is a call to some of those to the large spectroscopic survey folks out there. I don't know if anybody are on this call, but I do have some collaborators I can chat with. There are plans to do, things beyond DESI. So they might help with those samples, but the low redshift sample for sure, yes. And what the low redshift sample will do will help with the resolution problem here. So the closer these galaxies are to us, the more we can probe down into the core and, overlap with a lot of the sort of more traditional CGM probes like absorption line studies and even potentially some X-rays. I think one of the things that'd be really neat to do is get sort of E Rosita plus, there's this nice E Rosita sample out there. I think it's probably fairly straightforward to get a thermal SE signal given the public data that's out there from the same sample. So that's something that could be done. Maybe I'll have time in the next month to do it on sabbatical, but we'll see.
Okay, so we're at the hour. So thank you again to our wonderful speaker, Nick. And just as a reminder, the next seminar is going to have a slightly different date and time, October 31st, Halloween at 4:30 Eastern time. So you can check we'll send out the usual emails on the list about it. But thanks everybody, and we'll see you next time.